All right, so chapter 2 is not everyone's favorite chapter, but we have to talk a little bit about chemistry to understand biology. Um, let's we'll see here the exhaust released by a car in Boston and how it contributes to the death of coral in the Great Barrier Reef of Australia. And that has to do with a chemical process. So understanding chemistry will help us understand a little bit of biology. Biology and society, nuclear medicine. So, radioactivity is the emission of high energy particles. It can kill cells by damaging DNA. Some radiation can be medically beneficial, like helping to treat cancer. Radiation therapy, however, does expose only a small part of the body to a precise dosage of radiation, but understanding the chemistry of radiation is essential to understanding biology. Here we have this PET scan of a human liver highlighting areas of diseased tissue. That's the radioactive vision. So let's talk a little bit about chemistry. I'll try to keep it really brief and focus on the things that I want you to focus on. In general, especially in this chapter, I want you to focus on defining key terms. So if you take any biological system apart, you'll eventually end up at the chemical level. Matter is anything that occupies space and has mass. Mass is a measure of the amount of material in an object. An element is a substance that cannot be broken down into other substances by chemical reactions, and all matter is composed of chemical elements. We organize the elements in the periodic table, as shown here. And the periodic table is organized into very specific kind of rows and columns called groups and periods. And each element has the element symbol, which is the abbreviation of its name. This is carbon. The atomic number, which gives us the number of protons, and then the atomic mass, which gives us the mass average of that element. So you can see abbreviations of all the elements shown here, from chlorine to mercury to hydrogen to sodium to potassium and so forth. Of the 92 naturally occurring elements, 25 are essential to people. Four of these elements make up about 96% of the weight of the body. Trace elements are required in only very small amounts, and elements will combine to form compounds, which are substances that contain two or more elements in a fixed ratio. Here we have the chemical composition of the human body. Most of the human body is made up of carbon, a lot of hydrogen, of nitrogen, and then you can see kind of what makes up the rest. So mostly oxygen, hydrogen, and nitrogen make up our body. Diet and goiter. So goiter was formed when your thyroid gland enlarges, and you kind of see this bulging area in this woman's neck, and that's due to a decreased amount of iodine. Iodine is required for your thyroid cells and your thyroid gland to function. So years ago, iodine was added to salt, and you can still buy iodized salt in the grocery store, and that kind of keeps some of these thyroid problems at bay. And that is iodized salt and how it relates to goiters and the thyroid gland. Atoms. So each element consists of one kind of atom, which is the smallest unit of matter that still retains the properties of an element. Atoms are composed of subatomic particles. Protons are positively charged, an electron is negatively charged, and a neutron is electrically neutral. So here we have an atom, specifically the helium atom, which in the nucleus has two protons and two neutrons, and around it, kind of surrounding it in a cloud, are the two electrons. So that is kind of the structure of an atom. The protons and neutrons are in the nucleus, the center, and the electrons surround that nucleus in electron cloud. Atoms of a particular element have the same unique number of protons, and this number is the element's atomic number. And an atom's mass number is the sum of the number of protons and neutrons in its nucleus. An isotope has the same number of protons and behaves identically in chemical reactions, but they have different numbers of neutrons. And a radioactive isotope is one in which the nucleus will decay spontaneously. So how effective is radiation in treating prostate cancer, which is frequently diagnosed among American men? Common treatments are surgery and radiation. Studies of the effectiveness of different methods, such as surgery and external radiation, are problematic because some groups of patients are not controlled at all, but it would be still unethical to withhold a treatment from those cancer patients. So in radioactivity, radioactive seeds can be inserted around a prostate tumor to try to decrease that tumor of the prostate gland. And you can see years after treatment and the percentage of patients whose cancer did not progress. You can see the seeds, the surgery, and the external radiation, and how really the seeds and external radiation kind of have the highest. Even after 10 years of treatment, the cancer did not progress with those seeds. So pretty interesting ways of treating prostate cancer. Chemical bonding and molecules. So only electrons are directly involved in chemical reactions. And the number of electrons in an atom determines the chemical properties of that atom. A chemical reaction enables atoms to transfer or share electrons, and these interactions usually result in atoms staying close together, held by attractions called chemical bonds. When an atom loses or gains electrons, it becomes electrically charged, and an ion is the atom or molecules that are electrically charged as a result of gaining or losing electrons, and an ionic bond is formed between oppositely charged ions. Compounds such as table salt that are held together by ionic bonds are called ionic compounds. And I'll let you guys look at this animation of ionic bonds on your own. You can click on it in the PowerPoint that I link in the module section. So ionic bonding occurs when electrons are transferred, and this is a sodium ion and a chloride ion forming the sodium chloride molecule, which is table salt. A covalent bond forms when two atoms share one or more pairs of electrons. Covalent bonds are the strongest of the various bonds, and they hold atoms together in a molecule. And take a look at that animation of covalent bonds in the PowerPoint. Alternative ways to represent a molecule, we can draw a molecule via their electron configuration, where we show an oxygen, a carbon, and two hydrogens. This is formaldehyde, where the molecular formula is shown here with one carbon, two hydrogen, and one oxygen. We can draw it out using the structural formula, where each line signifies a bond. So this would be a double bond, and those other two would be single. The space-filling model or the ball and stick model, different ways to represent a molecule. Hydrogen bonds. So a molecule of water, for example, consists of two hydrogen atoms joined to one oxygen atom by covalent bonds, but electrons are not shared equally between the oxygen and hydrogen atoms, and that causes water to be a polar molecule, which means it's one with an uneven distribution of charge. That means that one end of it is negative and one end of a water molecule is positive. And this polarity of water results in a very weak electrical attraction called hydrogen bonds between neighboring water molecules. And this is a hydrogen bond. It's a bond between neighboring water molecules that forms due to the polarity of the water molecule itself. And there's a look at water structure animation. Chemical bonding and molecules. I'm going to have you guys do these checkpoints on your own, because when you fill out your reading guides, it'll take you through some of these similar questions. Chemical reactions. So cells are constantly rearranging their molecules, and such changes in the chemical composition of matter are called chemical reactions and include the reactants, which are the starting materials, and the products, which are the end materials. And chemical reactions can rearrange matter, but they cannot create or destroy matter. Which major theme is illustrated by this action? Cells are constantly rearranging molecules by breaking existing chemical bonds and forming new ones. This would be pathways that transform energy and matter, and that is what is going on here with these chemical reactions. Water and life, I'll let you guys read through this and how life in water is incredibly important to life. Modern life is still tied to water, and your cells are composed of 70 to 95% of water. And the abundance of water is a major reason that Earth is habitable. And the polarity of those water molecules and the hydrogen bonding that results explain most of water's life-supporting properties. Water molecules stick together as a result of hydrogen bonding, and this tendency is called cohesion, and it's much stronger for water than other liquids. Trees depend on cohesion to help transport water from their roots to the leaves, and surface tension is a measure of how difficult it is to stretch or break the surface of a liquid. Hydrogen bonds will give water an unusually high surface tension. You can see a raft spider walking on the water due to that surface tension, so it can't sink. How water moderates temperature. So because of hydrogen bonding, water has a stronger resistance to temperature change than most other substances. And because heat is first used to break hydrogen bonds, water absorbs and stores a large amount of heat while warming up only a few degrees. And conversely, when water cools, hydrogen bonds will form, which is a process that releases heat. And this evaporative cooling occurs when a substance evaporates and the surface of the liquid remaining behind cools. You can see that evaporative cooling happening there. Floating, ice floating. When water molecules get cold enough, they move apart, forming ice, and a chunk of ice floats because it's less dense than the liquid water in which it's floating. Floating ice acts as an insulating blanket over liquid water, and this allows life to persist under the frozen surface. If ice did not float, ponds, lakes, and even the oceans would freeze solid. So that is how ice floats, because ice is less dense than the water below it. A solution then is a liquid consisting of a homogeneous mixture of two or more substances. The dissolving agent is the solvent, and the dissolved substance is the solute. And when water is the solvent, the result is an aqueous solution. So we can here see sodium ions and chloride ions in a solution of water. All right. The polarity of water molecules helps explain water's ability to support life. And that would be the relationship of structure to function, because the structure of those water molecules relates to its function. Acids, bases, and pH. So a chemical compound that releases hydrogen into a solution is called an acid. And a compound that accepts hydrogen and removes them from a solution is called a base. And to describe the acidity of a solution, chemists use the pH scale, which is a measure of the hydrogen ion concentration in a solution, and a buffer minimizes changes in pH. So here we have the pH scale. Pure water is 7, so completely neutralized solution would have equal amounts of oxide and hydrogen. Human blood is slightly basic. It's about 7.4. More basic would be seawater, milk of magnesia, ammonia, bleach, oven cleaner. And then moving down on the acidic side, anything less than 7 would be urine, black coffee, tomato juice, grapefruit, lemon juice, battery acid, and eventually hydrochloric acid. Ocean acidification by atmospheric CO2. We'll talk about how CO2 in the atmosphere can go through a chemical reaction in the water to lead to carbonic acid in the oceans, and that can lead to some ocean acidification. All right, I'm going to skip over some of those, and then I think I'm going to kind of pass over, and I think we're done. Okay, so we'll see you for chapter 3, guys. Take care, and thank you for listening.